Oh, that's my, okay. Oh, okay. You made it go away right when I record. Yeah. Okay. All right. So we'll get started now. I'll bring the camera up in a second. Sorry, I'm trying to get demos because the complaint was I blow up too many hydrogen balloons. The complaint was, do I have anything else up my sleeve? So yeah, well, let's try for some other demos that I have here. So they're doing their magic, setting it up. But we still have to finish chapter 11. We have like no slides left in chapter 11. It's just kind of some recap and talk about catalysis for chapter 11. And then that concludes, don't worry about it. Thank you. That concludes all of the material for midterm 3. Wow, there's not a lot of people here today. Is there like an exam or something going on, sleeping? Yes, oh, go ahead. Okay. Exam on Monday, yes, our midterm 3, and we'll finish that material today. I do want to announce that I have my Zoom session tonight at 6:30. Did you see that in your calendar? Yeah, it's in your calendar. So that Zoom session is tonight at 6:30 in McPherson 1045. So it's on the calendar. I couldn't book the CBEC room. There's like an exam going on in there. So don't go there. There's an exam there. Go to McPherson 1045. So it's in your calendar. In that calendar page, you'll see the Zoom link, and you'll find the document that I'll work on during that review session tonight. And I'm going to record it, and I will post it on that same page for you guys to look at over the weekend. Good. So hopefully that Zoom, not the Zoom session, the Kahoot session really opened your eyes to the kinds of questions that I can ask on the exam. It's all fair game, all of those questions that were on there. So, you know, the more questions that you see and you practice, the more comfortable you'll be on the exam. You'll see that there's not many ways I can ask certain questions. Like if it's a coffee cup calorimetry question, there's only one way I can ask it. And there's, you know, a couple places where you can really screw up, all right? But if you practice the strategy within there, you know, predicting the sign of delta H, you'll be in better shape for questions like that. Basically, I can only ask questions of a certain way. And once you see it 3-4 times, you'll be more comfortable there. All right, so the review session with me is tonight at 6:30. Bring your dinner, it doesn't matter, it's very informal. Okay, so midterm. Anything else? No, I think that's it. So we will finish chapter 11 here and then start chapter 12 because we do have to cover chapters 12 and 13 before the final. And I think we only have about 9 lecture days left or something like that. All right. And we'll do a little skipping around in chapter 12. So I can prepare you for the LCP lab that you're going to do next week after lab or after the midterm on Monday. And do remember, all of the resources for midterm 3 are posted already. So it's up to you. It's all in your hands now. Okay. My work is essentially done. All right, so we left off talking about catalysis in the chapter of chemical kinetics, so how fast reactions go. We studied 3 different ways to get a rate law for a chemical reaction, the 3 different ways, and all of them are fair game for the exam. And I think, you know, me and Matt wrote the exam, all 3 are represented in some way on the exam. The first one was the method of initial rates, where you look at experiments and you see, okay, this reactant doubles in concentration, the reaction rate doubles, so that's first order, things like that, where you look at how the initial rates change with different experiments. The second way we did determining rate laws is through the graphical method. So we use the integrated rate laws. Depending how we graph concentration versus time tells you the order of that reactant. And then the third one was my favorite, mechanisms, where you deduce, you know, you have different elementary steps for a chemical reaction. You look at the slowest step, and that's what dictates your overall reaction rate. If there's an intermediate present, you have to get rid of it using the fast step. And so now we're in the last part of the chapter where we just will look at catalysis, other ways we can speed up reactions. So what we saw earlier was that speed of reaction, reaction or rate constant is related to activation energy for a reaction. That we saw, okay, that, you know, this first step is obviously the slow step in this reaction because that first hill is real big. The next hill is real small. So that next step, the second step is going to be really fast, but the first one will be really slow. So the other way we can speed up a reaction, you know, we can heat up a reaction, that'll speed it up, but also if we lower the activation energy somehow for a reaction, we can also speed up a reaction. And so that's by introducing a catalyst. So how catalysts work, well, first we need to think about what phase they're in. Catalysts can be in the same phase as your reactant. So something like an all gas or all aqueous phase, those actually have better collisions. Those types of catalysts work better. But industrial processes, heterogeneous catalysts are more prevalent because it's easy to just drop a solid into like a reaction like vessel, to just drop a solid in versus to get it to dissolve and interact with your reactants fully. So then you get like really good collisions there. So heterogeneous catalyst would be like dropping a solid into something that's all gas phase. So basically the catalysis is happening on the surface of that solid, or you could put a solid into an aqueous solution. So those aqueous dissolved bits, again, all that reaction happens on the surface of the catalyst. So in general, why catalysts speed up reactions is because they're lowering the activation energy of your specific reaction. There's a new pathway that it's taking, actually a new mechanism that it's taking to get to the products. And so catalysts are different than like intermediates or reactants, because in a reactant, you know, it's you start with it, it's a substance you start with, but it's consumed fully in the reaction. A catalyst is a little bit different. It may look initially like a reactant where it's consumed at the beginning, but you always produce your catalyst again as a product before the end of your reaction. And so when you have your catalyst as a reactant and a product, they cancel out. So you don't see it in the overall reaction, but you still need it to be there in order for the reaction to go forward. So the thing is, catalyst, you might think it's a reactant in the first step, but a product usually in the final step. So it's not consumed overall. All right, and so enzymes are our body's catalysts. But in this class, we don't care about our bodies, we care about cars. And so that's why, you know, I don't have my slide, but we'll talk about catalytic converters here in a slide. So looked at this reaction, high activation energy. This doesn't happen, the decomposition of hydrogen peroxide doesn't happen in your medicine cabinet. We know because your bottle of peroxide doesn't blow up spontaneously in that cabinet. So instead, you know, we wait for peroxide to work by introducing a catalyst, such as our blood. So when you put hydrogen peroxide like on your skin or whatever, your blood and your like proteins and enzymes react with that peroxide to break it down to make products. So our bodies are acting as a catalyst, giving a different pathway, you see, so an overall lower activation energy to get to our products. And so we identified our catalysts in this reaction as both bromide and H+. So HBr, acid, essentially, is our catalyst because it's consumed in the first step and then it's produced in the last step. All right, and then I think we identified an intermediate as well, would be Br2, because it's produced in the first step and then also consumed in the second step. So it only kind of exists in the middle there. Neither the catalyst or the intermediate shows up in your balanced chemical reaction. All right, and so I mentioned enzymes, our body's biological catalysts. Our enzymes are fueling energetically not favorable reactions forward. That's the purpose of enzymes, lowering those activation energies. So reactions happen in our bodies on like our lifetime time scale. So how enzymes work, again, we're lowering activation energy, but we're also speeding up reactions by other ways. If we look at the Arrhenius equation and see how rate constant changes with different factors, enzymes you know, they touch on every single one of these factors if we remember the definitions of these factors. So enzymes, biologists use fancy words that are slightly different than chemists. Chemists use words like products and reactants. All right. So biologists, they use words like substrate. All right. So substrate means your reactant. And then I think product is the same word. So they oftentimes talk about substrates to mean reactants. Not that you need to know that. It's just sometimes when we talk about your reactant binding to your enzyme, because a lot of this is surface chemistry, where those collisions happen. Biologists call it a enzyme substrate complex, when your complex is bound to your reactant. So that's specific to biologists, but in the chemistry and catalysis community, we just use normal words like catalyst and reactant, and that's fine. It's just different for biologists. So basically, once your enzyme or your catalyst binds to your reactant, your substrate, it does a couple things. All right. So what that enzyme does is grabs your substrate, grabs your reactant, and brings them really close together. So if it brings your reactants close together, it improves the collisions. So by bringing together your substrates or your reactants, you increase your frequency factor, the amount of collisions that happen. If you're at the Kahoot thing, I really liked this meme that I put on there just for a second. It was, who was it? Who was that boxer guy? And he had two pigeons. Mike Tyson, yeah, he had two pigeons and it said catalyst be like, and he was making the two pigeons kiss. That's this, all right? Catalysts bring reactants together, like Mike Tyson brings two pigeons together to kiss one another. That's essentially what catalysts do. Bring those reactants so they collide very well together to make a product, to make a chemical reaction come together. Also, what a enzyme does is bring your two reactants together, but orient them in the right way to make a proper collision, to make a proper collision to lead to a product. So it's not just bringing the two reactants together, but bringing them together to make a good collision that will lead us to a product. So again, Mike Tyson and the two pigeons, bringing them together, not butt to butt, but like face to face, so that they kiss each other and make a product. That makes sense? Or is that too much? I laughed at that like probably for too long. All right, and then the last one is when your enzyme binds to your reactant in biological systems. What that does is weaken a lot of the bonds in the reactant. So if you pre-weaken the bonds in your reactant, in your substrate, it lowers the activation energy and leads to a more, leads to an easier time to get to our products, a lower activation barrier. So these first two, the reasons that reaction rate increases is because frequency factor increases. This last one increases reaction rate not because of frequency factor, but because it lowers the activation energy of the reaction. So bond energy of the substrate, that enzyme pre-weakens the bonds, so it's easier to get to products. Orientation and proximity, that's like our Mike Tyson catalyst, bringing the reactants together. So you're more likely to have those sufficient collisions. All right, so those are enzymes, but people don't care about those. So let's talk about what we do care about, cars, and not the human body. And so our catalytic converter in our car is, one of the, I guess, most common catalysts, I guess, that people think about when you think of catalysis. The catalytic converter, it's a very expensive piece, component of our vehicles. So just to put it into perspective, so this is what a catalytic converter looks like. The type of reaction that it facilitates or makes speed up is a oxidation reduction reaction, which we will actually talk about in chapter 13. So we're not quite there yet, but just know that it catalyzes a certain type of reaction, reduction and oxidation. So there's about 5 grams of rare earth metals inside a catalytic converter. It's not a lot. So it's mostly platinum, palladium, and rhodium. And so those rare earth metals are kind of scattered along I think, aluminum dioxide frame, a honeycomb frame. So if you look at a catalytic converter, there's a lot of air pockets within it, because this is an example of heterogeneous catalysis. The catalyst itself is a solid, and all of the reactants that it's trying to catalyze are gases. So gases that come off of your exhaust system on your vehicle. And so the only way your catalyst will interact with those reactants, those gas species, is at the surface. So instead of, dropping in a hunk of platinum, where the only spot where catalysis can happen is on the surface, just like a sphere of platinum doesn't actually have a lot of surface area. So instead they make this honeycomb pattern to give more surface area to facilitate this electron transfer. It's all surface chemistry, right? So more surface area with a honeycomb pattern. All right. And so I think I just took this from like some car manufacturer or something. So you see that they don't have like proper subscripts and things. All right. So I think automotive engineers made this diagram, but I like it because it clearly shows what we're trying to catalyze. We're trying to take noxious fumes that come off of the exhaust system of our internal combustion engines, such as hydrocarbons, so uncombusted hydrocarbons. We put hydrocarbons in our gas tanks because we want to, combust them and make our cars go. But sometimes under certain conditions, you don't burn all of the hydrocarbons. So those just go out your tailpipe. So that's like dollars that you're just wasting. But also it's bad for the environment and health to have those hydrocarbons just go back into the atmosphere. So engineers just call it HC to stand for hydrocarbon. Other things in the exhaust gas are carbon monoxide. So it's an not as oxidized form of carbon. You get a lot of carbon monoxide with incomplete combustion in your vehicle. Again, if your vehicle is old or not running in tip-top shape, you can be exhausting carbon monoxide and different NO containing oxides, so nitrogen containing oxides, or what we call NOx gas. So NOx gas, so it could be something like nitrogen dioxide. That's really bad for the environment because NO2, right? NO2, come on. NO2, when you mix that with water, you get nitric acid. Or if you have too much NO2 in the atmosphere and it starts to rain, what do you think that turns into if it goes through a cloud of NO2? Acid rain, yes, so that's bad. Those are all bad things. And so that's why, it's basically the law in order to have passenger vehicles to have catalytic converters on them to convert all of these bad things, hydrocarbons, carbon monoxide, NOx, to water, carbon dioxide, and nitrogen. Those are all nice things that already exist in abundance in our atmosphere. All right, so that's the reactions that's being catalyzed. It's really hard to turn these exhaust gases into those better gases. So that's why we need platinum to catalyze it. And again, we have lots of surface chemistry on here for that redox to happen. And so a small detail here, okay, let's move this down here so you can see it, all right? So I mentioned there's three exhaust gases. There's NOx, there's CO, carbon monoxide, and there's uncombusted hydrocarbons. So there's a small detail here that I really like, but it kind of sucks that we haven't done redox chemistry yet, but that's okay. So I mentioned the three bad things: NOx, CO, and hydrocarbons. So in your tailpipe or in your catalytic converter, we need to reduce NO2 to nitrogen. So just believe me, right? We need to reduce, meaning NO2 needs to gain electrons to become N2 gas. So basically we see that electrons, reduction of NO2, is consuming electrons. You need to put electrons into NO2 to get it to reduce. Versus if we look at the other things, right? So that's what you see, gains electrons. We need to oxidize CO and we need to oxidize those uncombusted hydrocarbons. So what's interesting here with oxidation is that these substances are actually losing electrons. All right, so this is basically the products you're losing electrons. Oh yeah, I wrote it right there, losing electrons, right? And so the cool thing about redox reactions is that they always happen together. When something's reduced, something else is always oxidized, okay? Because electrons will always, try to complete this circuit. So you have something that's reduced, is gaining electrons. Where are those electrons coming from? They're coming from the thing that's oxidized, the thing that is giving off electrons. So you see we have this complete loop, that we have two substances that are being oxidized. They're both losing their electrons. Where do you think this electron's going to go? It's right now, it's sitting in the catalytic converter. Where do you think it's going to go? That electron is going to go to the reaction that's catalyzing the reduction of NO2. So you've actually made a complete circuit within your catalytic converter. So if you look at this, the different parts of your catalytic converter, there's 3 different chambers for these reactions to happen. You have oxidation reactions that are happening that are giving off electrons. So instead of those electrons going off and, doing whatever, those electrons are actually going to reduce NO2 gases to make N2. So we have that complete circuit, and I like that. And so the last detail here, which I think is really interesting, is depending on how much oxygen is you're sending through your engine. So running rich or running lean will actually change the ratio of how much reduction you're doing in your cat versus how much oxidation you're doing in your cat. So if you're off, that means that you're, what is this? If you're running lean, so you have too much oxygen, so you're basically consuming all of your fuel here, your converter is going to favor the reduction of NO2, all right? So basically you're going to be consuming all of these electrons, but if you're only doing reduction of NO2, those electrons, we have nowhere for electrons to come from because we actually have no hydrocarbons. So again, we need this complete system. We don't want to run lean. We also don't want to run rich, because running rich, you have incomplete combustion, too much uncombusted hydrocarbons. And so you're favoring oxidation. Oxidation is giving up electrons. Once you give up a bunch of electrons, those electrons have nowhere to go. There's no reduction reaction happening. And so, in a properly running vehicle and catalyst, you want to be running all 3 of these reactions. So you don't want to be running lean. You don't want to be running rich, because one oxidation reaction always comes with a reduction reaction as well. You want both of them to be running at the same time to be as efficient as possible. So I did a little bit of, I don't think this is in your book. I just thought it was interesting when I was talking about looking at catalysts and relating it to things we already talked about, like running lean, running rich, and it'll make a little bit more sense when we get to chapter 13 and talk about redox reactions. But the idea here is those electrons have to have somewhere to go. We need all of those reactions happening at once. Yes.
How does temperature affect like the
cat?
The catalyst reaction? I know your cars are like programmed when you start off to like hold a high idle to heat up.
Yeah.
So is that?
You tell me. Here, look. So how does temperature affect rate? So we're talking about the rate of converting those noxious fumes into better things, right? So yeah, the idea here is that catalysts will only work at high enough temperatures, and it really has to do with the Arrhenius equation. The Arrhenius equation, where if the temperature is high enough, now your particles have enough kinetic energy to get over that activation barrier. So, within the presence of the catalyst, you do lower that activation energy, but you still need enough energy in terms of kinetic energy of the temperature of your particles to get it over that hill. So both are still there. Temperature is still important within there. But yeah, I know, like when using cats, they usually say like get it up to like 500 degrees Celsius or something before it really starts to take off. So it all has to do with the Arrhenius equation. It says when T increases, rate constant increases too. Okay. All right. So there's a lot about catalysts. Maybe you learned something. I learned something making that slide. Okay. All right. And so, of course, we don't want NOx or hydrocarbons in our air because it contributes to bad things. So versus water, CO2, and nitrogen, much better. Good. Yeah, we're not in a, so I lived in Pennsylvania for a while and we had emissions testing, you know, yeah, so not in Pennsylvania, unless you're in a E-check county, but Franklin County isn't. So in Pennsylvania, we had to do emissions checks where literally they just put like a tube on your exhaust and measured how much NO2, how much uncombusted hydrocarbons you were sending off your tailpipe. And if you didn't, and if you failed, then you wouldn't get your registration for the year. So my dad always had me go to a shady friend to do our emissions check. And so I drove a real old car. It was a 1988, so the car was older than me, 1988 Geo Prism. It had like bullet holes in it, but it was so fun. It was a great car. I loved it. But one year, like I wasn't gonna pass emissions. And so the guy, the shady guy, he told me, go drive the county over and then drive back. Right, so warm up the cat like really high. He's like, all highway. He's like, do all highway, come straight here. I'll do the test one more time right after you like drive for an hour and come back. And then I passed. And that was the last year I could pass. Then after that, we had to get rid of that car. It was my favorite car though. But it had very bad emissions because 1988. All right, so the technology just wasn't as good. Oh, also, because all of this is surface chemistry in your cat, if you screw up your surface somehow, you reduce the efficiency of your cat. So something that can reduce the efficiency of your cat is something like lead. Because when you fill up your gas tank and you put like 87 or something into your gas tank, what do they call that? Unleaded gas, because they used to put lead in it, all right, in order to improve octane rating, but now they don't, but they call it, so they still call it unleaded. But if there was lead, that it would spoil your cat. Okay, there you go. And I mean catalysts. Okay, all right, so we're done with chapter 11. Good. All right, so we're gonna move on to chapter 12 and hopefully do some demos here. All right, talking about cats. We had a lot of dog today, so we had to talk about cats. Okay, all right, so in chapter 11, we talked about rate constant. Rate constant we called small k, small k. This chapter, we're going to talk about big K, equilibrium constant. These are different, but they're related, I promise you. Because the idea here is like we can calculate the rate constant for forward reaction, all right? When the forward reaction is really high, you make a lot of your product, you consume your reactant, stuff like that. But the idea here is not all reactions just happen in one direction. Some reactions actually call what we call as an equilibrium, where both the forward and the reverse reactions happen at the same time. That's called chemical equilibrium. And so here are some analogies, all right? If I had like a vat of water and I had water going in, but I also had a spigot to make water go out. There could be a certain point, right, where what we look at, when we look at the vat of water, the water level stays the same. The only time that will happen is if the rate of water coming into the vat is the same as the rate of water leaving the vat, right? So rate in equals rate out. We should see no net change in the observation. Another analogy would be like someone walking up an escalator. If this person's rate, you know, of walking up is the same rate as the escalator is moving down, if we're looking at afar, we will see that person not move. They'll just stay in one place as long as this these rates, these overall rates are equal to one another. And that is the basis of chemical equilibria, when we've achieved the forward and reverse rates being equal to one another. And recall, how we get rate is from rate laws. So we see that K, small k, is related to big K in a way. So why we care about chemical equilibria, back in chapter, I forget, 3 or 4 or something, we talked about reactions that have like this kind of arrow. Remember, just like one arrow, versus we talked about weak electrolytes, I think in chapter 4, I don't remember, or maybe chapter 3, when talking about strong versus weak electrolytes. Weak electrolytes had this double arrow. Do you remember talking about that? That double arrow means that both the reactants and product side exist at the same time, versus this like full forward arrow means that just the products will exist when that reaction moves forward. And so we are going to explore this. Reversible reactions, reactions where both the products and reactant side exists at the same time. This chapter has 3 homework sets. It is quite long because this chapter is actually 3 chapters in 1220, and I have condensed it to 50 slides. All right, so let's go. All right, so equilibrium constant, big K. This is big K, is actually is easier than you think, big K. I think it's actually more intuitive than rate constant, small k. Big K represents the ratio of products over reactants of your species when you have achieved equilibrium. Equilibrium is when you have your staircase thing, right? And the lady's walking up and the staircase is moving down, right? At chemical equilibrium, if we were to measure the concentration of everything and get a ratio, that's what equilibrium constant represents. So generally, I like to say K is equal to products over reactants. We just want to make sure that we put the appropriate superscripts and stuff on it where the coefficients become superscripts. So for example, if we look at this reaction, the K for this reaction would be the concentration of HI squared over the concentration of H2 over the concentration of I2. And that's what you see right here. Here's K. That's written right here. So HI needs to be squared because of that coefficient, right? So the idea here is equilibrium is achieved once your system reaches a constant concentration, right? So from the outsider perspective, it looks like, oh, the reaction isn't changing, concentrations aren't changing, but it actually is. It's just that the forward rate is equal to the reverse rate, so we don't see this overall change. All right, so that's the big idea with equilibrium constant, right? And so here's like an example of table values where in experiment 1, I initially put reactants present. And so when we let the reaction go, we see that we make some products, and at equilibrium, if we take the ratio of products over reactants, we get 51.5. Or in experiment 2, where we just put HI, a product, in the vessel, let the reaction goes in reverse. Again, if we measure equilibrium concentrations, we get the same number. So equilibrium constant is an intensive property of a reaction. Doesn't matter how much stuff is there. It's intensive. You'll always get the same ratio as long as you're at equilibrium. All right, so the idea here with this equilibrium constant, only things that have concentrations can go in there. So what that means is only things that are aqueous, so dissolved in water, or things like gases go into the equilibrium constant. If something's a liquid or a solid, you don't put it in there. And the reason is solids and liquids, because they're so dense, densely packed with particles, they typically don't change their concentration with time, but gases and things that are dissolved do. So yeah, in practice, we only put things that are aqueous or a gas into our K expression, right? And so based upon that, our K expressions, there's actually 2 different kinds that we can use, Kc and Kp. Kc is where we put everything in terms of concentration units, so molarity. Kp, what do you think P stands for? Pressure, yeah. So remember, we can put gases in our K expression. So if you are working with gases, sometimes it's easier to work with Kp because you want to put P pressures in our K expression instead, right? But you still set up your K expression the same, products over reactants. It's just Kc uses concentrations, Kp you use gases, all right? Okay, so what is K? Relate it to kinetics, okay? So remember, K, we've reached chemical equilibrium when the forward rate is equal to the reverse rate. So let's look at this chemical process, right? It's an elementary reaction. Let's remember rate laws. So if this is an elementary reaction, I can write the rate law for the forward direction to mean rate forward equals Kf times the concentration of reactants. Do you remember how to do that? Yeah. We can also write the rate rate law for the reverse reaction. The rate law for the reverse reaction is K, the rate constant for the reverse reaction, times the concentration of products. All right. So I've just essentially written a rate law for the forward reaction and the reverse reaction. Remember what chemical equilibrium is. It's when the forward rate equals the reverse rate. So essentially, I can just set these two equations equal to one another. Or it's this equation, that equation. That is what chemical equilibria is, where we set the two rate laws, forward, reverse, equal to one another. So cool. What's the point here? I have this expression that relates K forward and K reverse and concentrations of things. Well, if you look closely and rearrange things, this is what you'll see. If you rearrange things, all right, forward rate equals reverse rate. If I put together my rate constants and I push the concentrations of other things to the other side, I can rearrange things to say, oh, the ratio of the forward rate over the ratio of the reverse rate equals the concentration of products over reactants. So your equilibrium constant, big K, is actually the ratio of your rate constants of your forward and reverse reactions. That's what it is. So these two chapters, though they may seem like they're different, they're actually not. All right. That K, our equilibrium constant, is related to our rate constants and therefore related to concentrations of reactants or products over reactants. I will say we will care more about this expression, products over reactants, than the rate constant part, but we'll come back to that. I'll bring that back here. All right, so based upon this example, all right, I just told you that chemical equilibrium, our equilibrium constant, is equal to the ratio of the forward rate over the reverse rate. What can you tell me about that equilibrium constant? Is it a big number or a small number based upon this graph? It's a big number or a small number. You should be able to tell me what the magnitudes of rate constants are. Rate constant for the forward reaction, is it fast or slow? Compared to the reverse reaction. Ask yourself, stand on this hill, you stand right there versus stand right there. In which direction are you going to go over the hill faster? The reverse reaction, right? So that means the reverse rate constant is a bigger number. So what does that tell you about the value of K, big K, equilibrium constant? It's going to be a small number. Yes, it's going to be a small number. So what's the significance of that? If this is equal to products over reactants, are you going to have more products or reactants present at equilibrium? If K, big K, is a small number, you're going to have more reactants because K is a small number, because you have a big number in the denominator. All right. And so I like to think of it, if we look at this chemical reaction, it's endothermic. I like to think, okay, if I had 100 children and I put them on this playground and I just let them run wild, you know, sometimes they go over the hill, sometimes they don't. If I come back a little bit later and I look at it, they're probably, most of them, more of them will probably be on the low energy side, right? That you'll have more reactants present at chemical equilibrium because that's the low point. And that's essentially what our relationship between rate constant and this new idea chemical equilibrium is, and products over reactants. All right, so that's where we're coming from. So now let's actually do some calculations and then we'll do some cool stuff here. All right, so remember K, big K, is products over reactants. So let's go back to our favorite evil guy, the Born-Haber process, which actually is a chemical equilibria. And let's write the Kc. So Kc means what? What's the C mean? Concentration. So that means the units of stuff in the expression need to be in molarity. So when writing the expression, I just remember products over reactants. So I'm going to write the products, NH3, concentration. So I'm going to use the brackets. But what's missing? I also need a 2 because there's a 2 coefficient. I need a 2 exponent. Products over reactants. So there's my product, then my reactants, N2, H2. Concentration. All those gases can have concentration. Moles per liter right? Moles of gas per like volume of gas. Yeah. All right. So what about the Kp expression? How is that different? Is it any different? Not really. It's just that we need to be working in pressures instead. So to make it clear that we're using pressures, I'm going to say, okay, the partial pressure of NH3 squared is in the numerator, and then the denominator, it's N2 pressure of H2. So we see that it's basically the same, all right, just pressures. Sometimes these values are different from one another for the same chemical reaction, and we'll look at and see why in a little bit. Okay, so there's our favorite guy. All right, so let's do a couple conversions and then we'll move on to some cool stuff. So let's see the significance of this. So let's work with the Born-Haber process again. Let's say that you let this reaction go, and at equilibrium, these are the concentrations you measure. All right, blah, 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 blah. All right, so since this is at equilibrium, they should fit our K expression. So we should be able to plug these numbers into that K expression we just got and plug in those numbers and calculate what K for this reaction is at this certain temperature. So let's just remind ourselves, this is NH3 squared over N2 times H2. And I got this from the balanced chemical reaction. All right, products over reactants. And now I'm just going to plug in those numbers. So NH3, 1.40 molarity squared over 0.3, that's coming from nitrogen, 0.9 coming from hydrogen. And I'll point out, K is actually unitless. It's unitless. We have a lot of molarities jumping around and stuff, but it is unitless. We just report it as one number. And hopefully when you put that in your calculator, 1.4 squared over 0.3 over 0.9 is something like 9.0. Okay, so just believe me or put it in your calculator, whatever. Okay, so let's kind of do it a different way here. What would the NH3 concentration be at this temperature if we measure a concentration of nitrogen to be that and hydrogen to be that? And so with this question, it's based upon the idea that we now know what K is, but we're just solving for this new component. So we know what K is, I know what N2 is, I know what H2 is, so I can just go in and back calculate that missing piece, since now I do know what K is. So K is equal to 9.0. So I am solving for the concentration of ammonia given these conditions. So N2 is 0.6 molarity, and hydrogen is 1.8 molarity. And so if you solve for that, you see that the ammonia concentration you need in order to reach chemical equilibrium to achieve K is something like 5.6 molarity. All right, and so do know that it's squared. So make sure that you do the appropriate algebra to get that unknown term. I'm not going to do it. Okay, so do take the square root of that. All right, so that's K. If you have equilibrium concentrations, you know what K is, or at least you can calculate it if you have the balanced chemical formula. So let's look at disrupting K. So I'm actually gonna, oh wait, no, we're actually gonna keep going. We're gonna do 2 more slides and then we'll electron tunnel. All right, so we just calculated Kc, so let's convert to Kp. All right, so C stands for concentration. You're working in molarities. Molarity, or big M, is equals to moles over liters. So if we look at like the Pivnert expression, all right, for gases, we can actually rearrange some things and say N over V equals P R, P over RT. Is that right? Yes, that's right, yeah. Okay, so N over V equals P over RT. So what does that mean? It means N over V, N is what? Moles, V is volume. So to me, that sounds an awful like molarity. So what we see here is that molarity is proportional to pressure with this RT term. So if we know the K expression for something, so K equals for this reaction, NH3 squared over N2, H2O3. Oh my gosh. You guys didn't. I missed that 3. This isn't balanced. Oh my gosh, guys. This reaction's not balanced. All right, let's just go back real quick. That's what happens when I update these slides and then it's not balanced. All right, so let's go back real quick. Did anyone think that in your head that this reaction wasn't balanced? No, all right, yeah. So I forgot the 3 there in front of H2. I'm so sorry. All right, but it's no matter. That's probably why no one calculated it. I didn't see any calculators come out. All right, I forgot that 3 in the balanced chemical equation. All right, so sorry about that. So I'm missing that 3. Again, coefficients do become superscripts here. Whew, glad I caught that. Right, so these K expressions are contingent on having the balanced chemical equation. Right, and so yeah, sorry, I forgot that 3, but everything else should be okay. And those answers in the corner should still be right. Oh, I put the 3 there. Did I put the 3 there? Maybe. And so all of these are missing that 3. All those calculations should come out fine. All right, you should still get the same thing there when using the balanced chemical equation. All right, sorry about that. And then, because what are we doing here? All right, so because I wanted to introduce K and us converting between Kc and Kp. So how I've written this equation right now, this is Kc because I have brackets. I have brackets, they represent molarity. All right, so this would be Kc. So in order to convert this into Kp, what I would have to do is just convert all of these concentrations to pressures, which I can do with this relationship. Molarity equals pressure over RT. All right, so I could just move some things around and see, okay, pressure is equal to molarity times RT. I know the molarity, so it looks like I just have to multiply by RT for every single species in the K expression. So I can just simplify it because I don't want to do that like 3 or 4 different times. I don't feel like doing that. So instead we can use this equation that relates Kp and Kc. So see, we have that RT term in the parentheses there. So how many times we need to multiply Kc by RT depends on how many moles of gas we have. So we see that RT is taken to the delta N. Delta N is the number of moles of gas that change during this chemical reaction. So what we do to calculate delta N is we take the moles of gaseous products and we subtract the number of moles of gaseous reactants. So on the reactant side, I have 4 moles of gas. On the product side, I have 2 moles of gas. So it looks like I am losing 2 moles of gas in this reaction. All right, so if I tell you what Kc is, so I tell you that Kc is equal to 9.6. So Kc equals 9.60. I can calculate Kp from this expression. I can calculate it from this expression and incorporating delta N. So basically, again, just taking that RT term and multiplying the appropriate number of times. But again, if you knew the actual concentrations here and just switched all of the concentrations to ATM values, you should get the same number. It's just using this equation is easier mathematically. And mathematically, they are the same. So there you go. So let's calculate Kp. So we take Kc, 9.60 to the R. Which R should I use? Which R do you, oh, I already said it right there. Okay, so that's the R we want to use. Why do we, so we've just come from like entropy and free energy and stuff, and we've been using 8.314. Well, why do we want to use 0.08206 now? Because we're working with gases now, and we're using PV equals nRT, which is based upon that liter ATM version of K. So we're going to do that 0.08206 value times temperature, which I give you is 573 Kelvin. And we're going to take that all to the negative, all of that to the delta N. And in this case, it's -2. All right. And so that's what we get. Okay. So use the appropriate R, use the temperature that's given. inspect the balanced chemical reaction and see, oh, we're going from 4 moles of gas to 2, so delta N is 2, and you can just use that equation to convert between Kc and Kp. Okay, great. All right, so we talked a lot about K and calculating K, big K. So let's talk about understanding its significance and particularly its magnitude, because it can tell us a lot about a chemical reaction. So equilibrium constant is actually a number, and it actually changes with temperature. And we'll talk about why here soon. Hopefully that sounds familiar, a K changing with temperature, right? So if you remember, the general form of K is products over reactants. So depending on the magnitude of K, will actually tell us a little bit about the reaction. K, when it's large, if K is products over reactants and K is large, what do we have a lot of at equilibrium? Products or reactants? Products, yeah, because K is a big number, products is at the numerator. Versus if K is a really small number, what do we have a lot of at equilibrium? Reactants, okay? Because big number reactant on the denominator will make K a small number. And so we can relate K to the distribution of products or reactants at equilibrium. If K is big, lots of products. If K is really, really small, so like less than 1, lots of reactants present. All right. We can also tell us a little bit about the rate constants, that the rate constant in the forward direction is faster because that's how you make a lot of products. Or if K is really small, the reverse reaction rate constant is faster because that's what produces a lot of reactants. All right. So that's kind of putting it all together. So think about the magnitude of K generally as products over reactants. If you have a big K, lots of reactants. If you have a small K, if you have a big K, lots of products. If you have a small K, lots of reactants. That will get you out of trouble like 80% of the time in this chapter. All right, so we're gonna actually tunnel to slide 18. We're gonna skip all the calculations and then just go straight to the fun stuff, which is, and we'll come back to the calculations, I promise. We're gonna talk about Le Chatelier's principle, because now you know K. Big K, lots of products, small K, lots of reactants. So we're gonna talk about disruptions to chemical equilibria, and this will relate to your LCP lab. So the idea here is I like to think of chemical equilibria as this. Do you know what this is? Do people still play with these? A seesaw, yes. Sorry to be patronizing, but okay, sea salt. So chemical equilibria is where the seesaw is perfectly balanced. Okay, that's chemical equilibria. Forward rate equals reverse rate. All right. So what we're going to do is we're going to disrupt the equilibrium. We're going to add something or we're going to remove something and think about how can we achieve equilibrium again? How can we achieve balance again after we've made a disruption? All right. And I think using a seesaw analogy is fine. I actually call that my quick and dirty way to Le Chatelier's principle, but it's actually based upon something a little bit more concrete, numerical, and that's calculating Q, which is the same thing as K. All right. So essentially with Le Chatelier's principle and disrupting chemical equilibria, we are disrupting this. Forward rate equals reverse rate. Just for a moment, we are disrupting that. All right. So pretend we're at equilibrium conditions, all the concentrations of stuff equal K. What happens when we add some junk to our chemical equilibria? We disrupt K. So if we have new concentrations that are not K, not at equilibrium, we call that Q, or the reaction quotient. So reaction quotient are concentrations that are not at equilibrium. It's calculated the exact same way. It's still products over reactants. The only difference is that we're not at equilibrium. That's the only difference. So what's cool here is if we can compare the value of Q to K, we can actually predict which way the reaction has to shift. So again, remember, K is products over reactants, Q is products over reactants. So let's pretend if I tell you that K is equal to 2 and for some reaction, then you set up a reaction where Q is equal to 4. So what you put in the vessel, when you calculate concentrations and stuff, you get Q is 4. What does that mean? What does that mean? Both of these represent products over reactants. So I always like to put it over a fraction to clearly see what I have. So K is equilibrium. That's what I want to be at. But right now I'm at 4. So I have too much what? Present. Too much products. Yeah, I have too much products. So which way should my reaction shift to achieve equilibrium? To the reactant side. So just by looking at the numbers, you can predict which way a reaction has to shift. So some people like memorize this table, right? They see, okay, when Q is a reverse reaction happens, or when Q is smaller than K, forward reaction happens. I don't like to memorize that things. I just look at the numbers and I think, oh, Q is too big, too much products, gotta go in reverse, things like that. I don't memorize things. Okay, so yeah, Q tells us a lot of things. Which way the reaction goes to establish equilibrium. It actually tells us a little bit about the change in reaction rates. And so what we're gonna do is look at changes in the system where we add or remove products or reactants, where we change pressure and change temperature. So if you think about the analogy of the seesaw stuff, that's like the quick and dirty way to predict shift. It'll get you there 80% of the time. So we'll look at some examples. All right, so let's look at this reaction. All right, so A2 plus B2 gives us 2AB. If I tell you that K is 1.5, let's look at these pictures and see what's gonna happen. All right, so for this reaction, I tell you K is 1.5, but let's remind ourselves how to make a K expression. The K expression for this reaction, this chemical equilibrium, and it's balanced, I promise, is concentration of AB, but it has to be squared over concentration of A2, concentration of B2. All right, so, and the ratio of products over reactants is 1.5. So let's look at these pictures and predict what's going to happen. So I just went ahead and counted things for you very carefully. All right, so if you look here, I count 1, 2, 3, 4, 5. Oh, I actually counted wrong. 1, 2, 3, 4. No, that's 6. That's 6, right? 6 ABs, and then there's 1 B2, that's the blue one, and then 1 A2. So let's calculate Q. Remember, Q is the same as K. So this is going to be concentration of AB squared over the concentration of A over the concentration of B. So you tell me, what is the value of Q in this picture? I have the numbers. It's 6 squared over 1 times 1. So Q is equal to 36. So how does that compare to KC? If Q is 36, remember K or Q is products over reactants. So I have too much products. The reaction has to shift which way? The opposite way, which is which way? Towards to the reactants. Yeah, so remember, this is equal to products minus reactants. So in order to make that number smaller, if I go in the reverse reaction, I will consume products, so I'll make the numerator smaller, but then I'll also increase the value in the denominator. So it'll overall make the total number smaller. So it reaches that 1.5 that we want. So this reaction needs to shift to the reactant side, so to the left. Okay, so let's keep going. What is Q for this second picture? Can you do the math? So again, products over reactants, make sure you're using the correct K expression. What is it? Can you do the math in your head? It's 9/6, which is also equal to 1.5. So what does that mean? It means nothing. This reaction is nothing? No. It means that we have the perfect amount of reactants. We have the perfect amount of products already. So that also means that this reaction is already at equilibrium because Q is equal to K, the K that I defined at the beginning here. So this, we are at equilibrium in that middle picture, right? So that means that the forward rate and the reverse rate, they're overall equal to one another. So we won't see a net change in particles. We should always continue to see 3 ABs, 3 A2s, and 2 B2s, always. Okay, so we're at equilibrium. And so what do we think the last one's going to be? It's going to be different, right? And so when we calculate Q here, so it's going to be equal to 2 squared over 3 times 3. So that's equal to 4 over 9. So that's about a half, about. That's Q, it's about a half, right? And so if you compare that Q to K, again, I like to think in fractions. Q is equal to 0.5 over 1, K is equal to 1.5 over 1. So in this picture, in this Q picture, I have too much what present? Reactants. If I have too much reactants, that makes a small Q. So that means this reaction has to shift in what direction to achieve K? Forward. Yeah, if I make more products, it'll make Q bigger and push toward the product side. So that way. All right, so that's based upon those pictures. We just got Q to predict which way the reaction shifts. All right, okay, so that's Q. Now, Le Chatelier's principle is a little bit different, where we think about a system that's already at equilibrium and we disrupt it somehow. And we think, okay, how can it go back? This is where using the seesaw analogy really helps, right? So let's look at this reaction. All right, so the same one. I think let's use the seesaw analogy. All right, so we got a seesaw, whatever. Okay, that's not a seesaw. There you go. There's my seesaw. All right. Use your intuition with your seesaw. If I add nitrogen gas, right? So this reaction's at equilibrium. I'm all nicely balanced. If I add nitrogen gas, I push on this side of the seesaw, right? And now it's kind of like, it's like this, it's like that. I add nitrogen gas, I add a reactant. Which way does the reaction have to shift the material to make it balanced again? Forward. Yeah, so if I add a reactant, the reaction's going to shift in the forward direction, right? To move that seesaw back so it's nice and even. So if I add nitrogen, the reaction's going to shift forward. What if I add a product? What if I add ammonia? Which way is the reaction going to shift? To the reverse. We're going to move to the reactant side. Again, if you use the seesaw analogy. Are you following? Okay. What if I take this reaction and I add hydrogen? Which way is it going to shift? Forward. Yep. Add a reactant, it's going to shift forward. What we're actually doing is disrupting Q, and we're thinking, okay, how does Q need to become K again? But Le Chatelier is the quick and dirty way to do it. All right, so let me change it up. Okay, we're at equilibrium. I remove some ammonia. What if I remove ammonia? How does my seesaw change? If I remove ammonia, isn't it like that? And it like lifts the one side? Okay, so if I remove ammonia, how should the reaction shift to regain equilibrium? It's going to move in what direction? Forward or reverse? Forward, yes, because we removed a product. The chemical equilibrium is going to want to fill that void back again. So it's going to go forward. What if I remove H2? Which way is the reaction going to shift? Backwards, back to the reactant side to fill that void. So that's kind of the quick and dirty way to do Le Chatelier's principle. This is the real way to do it, all right? Because what we actually do is when we disrupt an equilibrium, we disrupt rate laws. So what are we doing? We're adding H2, all right? So we're going to add H2. You told me that Le Chatelier says when you add H2, the reaction shifts in the forward direction, that you make more NH3. But I want to prove to you that that is correct using rate laws. So remember, at equilibrium, the forward rate equals the reverse rate. When we add H2, the moment we add H2, how do we change K? We're increasing the amount of product. So Q, is it going to become more than K or less than K the moment we add H2? If we're increasing the number that's in the denominator, it's going to be, yeah, it's going to go down. So in that moment, Q is smaller than K. And so if Q is smaller than K, the reaction has to shift forward to make up for product because we made Q smaller. So that is all consistent with Le Chatelier's. But why does the reaction shift forward? That's the question. So let's look at the rate law. Remember, at equilibrium, forward rate equals reverse rate. So look at this rate law. The forward rate equals reverse rate. So the moment we add H2, Why does the reaction shift forward? Is it because the forward rate increases or because the reverse rate decreases? Look at the rate law. What are we changing at that moment? Hydrogen concentration. Where is hydrogen concentration? In the forward rate. So in that moment, because we've increased hydrogen, the forward rate becomes larger than the reverse rate for just that moment. All right, and that's because hydrogen's only in the forward rate law, right? And that's why the reaction does shift forward. So that's kind of like a behind the scenes thing, all right? Small detail of we've disrupted the equilibrium, we've disrupted the rate laws, all right? But you don't actually need to know that for just applying Le Chatelier's. You can just be like, oh, add reactant, push to products, and it's fine and dandy. Okay, so let's look at pressures, okay? Let's look at pressures. So pressures, this is specific for reactions that have gases in their chemical equilibria. So the quick and dirty way to do it is when you, and I have that right here. If the pressure of your vessel is increased, all right, so you're squeezing on your system. If you squeeze on your system, reduce the volume, increase the pressure, your reaction will shift to the side with less moles of gas to relieve that pressure. So I like to look at like this reaction. See how there's 1 mole of gas on the reactant side, 2 moles on the product side. If I squeeze on that chemical equilibria, the reaction is going to relieve itself by making less moles of gas. So I squeeze on it, this reaction is going to move to the reactant side because there's less moles of gas in this particular reaction. Okay, it depends on what reaction you're looking at. But we can also use Q. So in this example, I say, okay, K is equal to 4, and I just made up numbers. I say, okay, at equilibrium, A concentration is 1 ATM, B concentration is 2 ATM. So if I calculate the new pressures at a halved volume, the new pressure of A is something like 2 ATM because I've halved the volume. The new pressure of B is something like 4 ATM. And so if I calculate Q, in this case, it's B squared over A, it's 16 over 2, so it equals 8. So 8 is larger than K. So in this example, there's too much product. It shifts to the reactant side. So this is still consistent with Le Chatelier's. So we're using numbers to back up our claims, but the quick and dirty way is fine as well. So for the other way, all right, we squeezed on container, reduced volume, increased pressure, reaction relieves itself by going to less moles of gas. The opposite is true too. If we expand our vessel, we lower the total pressure of our system, the reaction will want to regain the pressure that was lost by moving to the side with more moles of gas, right? So if we did that to this reaction, right, we expanded it, this reaction is going to shift to product side because you can fill that void by those extra moles of B, essentially. And you can do the calculation yourself, and I think you will calculate the new Q is smaller than K, and you'll get the same conclusion. But this is, again, the quick and dirty way to do it is, okay, whether you increase or decrease the moles of gas, like through volume compression or expansion, you'll shift to the side of the reaction that will fix what you messed up, essentially, right? Okay. So in this example, we do have changing moles of gas, but not always. So there are some equilibria that are actually unaffected by volume changes, and that will happen when the moles of gas for a reaction remain the same. And the reason is because there's no way for the reaction to relieve itself of pressure effects. So for example, here, this first reaction, delta N is equal to +1, that the reaction as it progresses forward, you're gaining 1 mole of gas. So if I squeezed on reaction A here, if I squeezed on it and I increase the pressure, which way will this reaction shift? To the product side or to the reactant side if I squeezed on it? So right now I have more moles of gas on my product side. So if I squeeze on it, it's going to go to the reactant side. Yeah, it's going to relieve itself by going to the side with less moles of gas. And so same thing for the next one. So we see, oh, there's actually more moles of gas on the product side. So yeah, CO, And again, so if I squeezed on that reaction, this one, if it was already at equilibrium, you're going to make more solid because your pressure of CO2 is too great, right? And you're going to squeeze on it and it's going to push to the side with less moles. C, on the other hand, what is the change in N? It's something like -1. So this one, if I squeezed on it, it's actually going to move to the product side because there's less moles of gas there. So we see that the correct answer is actually D, because the delta N is 0. There's 2 moles of gas on each side. So if I squeezed on it, all right, increase the pressure, is there any direction that will relieve that increase of pressure? No, there is not. So that equilibrium remains unaffected by any compression or expansion. All right, so let's look at the last one here, Le Chatelier's principle. So disrupting equilibrium, then we'll do our demo, is temperature. All right, Le Chatelier's principle and temperature. So like I said, Le Chatelier, it's like the quick and dirty way to predict shift, but you're always right in the end, but right kind of for the wrong reasons. So we looked at adding a reactant or removing a product, how that shifts equilibria. We can actually treat exo and endothermic reactions similarly if we treat heat as a product or a reactant. We'll actually still get the same answer, but for the wrong reason. But that's okay if we're just trying to predict shift. So let's think about an exothermic reaction. Exothermic. Is heat a product or a reactant? Exothermic. You're only 50-50. It's a product. Yes, exothermic reactions. Okay. What's your favorite exothermic reaction? Combustion. Is heat, what is heat? Is it a reactant or a product in a combustion reaction? Why do we love combustion reactions so much? Fire, because that fire is Q coming off, leaving the reaction. All right, so it's a product. That's why we love it so much. So exothermic reactions, heat is a product. So I'm just going to put a little triangle there. Triangle is heat. Okay. So here's the quick and dirty way. Just treat triangle as a product or a reactant. So if I heat the vessel, I heat it, I'm adding triangle to the reaction. Triangle is a product. So which way does the reaction shift? Just treat it like any old product or reactant like we did in the previous examples. The reaction shifts to the reactant side. Good? Yes. So what if we cool the reaction? Cooling the reaction, you're removing triangle. You remove heat. So we're removing a product. So which way will the reaction shift? To the product side. That's it. That's it. So again, if you correctly identify where heat triangle lives when it's exo versus endothermic, just treat triangle as a product or reactant, you'll get there. Right? So based upon our observations here, is calcium hydroxide more or less soluble at high temperatures? What? Less, yes. Isn't that weird? That's weird. Usually solids get more soluble at high temperatures. Weird. Okay. All right, let's look at this one, endothermic. I think that is a question in your LCP lab, maybe. All right, let's look at this dissolution process. Potassium chloride goes to, potassium chloride, solid to aqueous. So this, we're just dissolving it. This is endothermic. So where do we put triangle? On the reactant side, yes. We have to give energy to make this reaction go. So to us, when we feel calcium chloride dissolve, what is it going to feel like? So let's review a little bit. If this was coffee cup calorimetry, which way should your thermometer go? Down, yes, that it absorbs heat. All right, so it's going to go down. All right, so it gets colder. So what happens when we heat the vessel? We're adding triangle. Which way will the reaction shift? The products. What if we cool the reaction? You're removing triangle, you're removing a reactant, so it shifts to the reactants. So is calcium or potassium chloride more or less soluble at higher temperature? more. Yes, it is more soluble. Okay, cool. All right, so again, quick and dirty way, just treat heat as a reactant. So let's look at this example, then we'll do the demo. Okay, so here's a chemical equilibrium. We have iron 3+, it's yellow, and it's in equilibrium with thiocyanate ion, and it makes a blood red complex here, and these are in equilibrium. So you can clearly see what side of the reaction is present, whether the solution is red or whether the solution is yellow. All right, so this is a really cool demo. You can put iron, like in iron 3+ in a test tube, you put tiny drops of thiocyanate in it and it becomes like an intense blood red. And it actually looks like blood. And the interesting thing is blood is made out of what? Iron. And yeah, so, you know, one of the components of this complex is iron. So we see iron has similar properties in different species. This isn't blood, but it looks like blood. Okay, so based upon this picture, all right, I did this experiment. I put this system in a hot water bath and a cold water bath. Tell me, is this reaction endo or exothermic? I would suggest putting triangles somewhere and testing it. If it matches your observations, then it's correct. If it doesn't, put triangle in a different spot and see if it matches your observations. So you tell me, is this an exo or endothermic reaction? And then whisper it to someone near you. Okay, does anyone want to share? What do we think it is? Not you. Yeah. Exothermic. I actually don't know. I need to test it. So where should I put my triangle? On the right. Okay, so let's test it. Heat it, it should turn yellow. Is that right? Yes. If I cool it, I should consume a product, so it should turn more red. Perfect. Yeah, so I agree that it is exothermic. Is that what you guys got? Okay, good. Yeah, and to me, it's just guess and check. All right, so let's do a demo where we disrupt equilibria. So I have a bunch of test tubes here. All right, I have a bunch of test tubes. The system that I'm studying is this cobalt system. So cobalt with a bunch of waters on it. All right, equilibrium. All right, I should have written this down beforehand. This is not balanced, but don't you worry. Okay, 2- and H2O. Okay, so the cool thing about this is that this complex is pink, and then this one over here is blue. So this is pink. This is blue. And then this is not balanced, but there's some other stuff going on here. So right now, what color is this test tube? Can we see? It's like purple, yes. So right now we actually see both at the same time. We see both the pink and the purple. So what I'm gonna do is disrupt the equilibrium. So the first one, this first test tube, and I'm sorry, I don't feel like setting up the doc cam, or maybe I should, I don't know. The first one, I'm gonna add concentrated HCl. So based upon that balanced reaction, if I add HCl, Cl, what am I adding to the equilibrium? A reactant. So which way should the reaction go? Forward. So the test tube should become what color? Blue. Yes, because I'm making more product. Whew. Oh, I need a hood in here. I hate this room. Okay, so let's see. Does that look blue? Yeah, so we just disrupted the equilibrium. Perfect. So see? All right, the next one, I need to add water. So look at the equilibrium. So remember, we're back at equilibrium because it's purple again. If I add water, what's going to happen? It should turn pink. It should turn pink. This is H2O. Let's see, does it turn pink? I hope it does. I didn't even mix it. See, so you see the pink at the top. Okay. Oh, here you go. Pink. All right, I didn't mix it, so you can still see the original purple on the bottom because I added a little bit of water. We pushed it to the reactant side. All right, next, I'm going to heat it. I don't know if this is hot enough. So we'll see what happens. I'm going to heat one and I'm going to cool the other one. let's see. Let's hope something happens. Okay. Go. All right. Nope. Okay. Lots of test tubes. All right. Heat it, cool it. Come on. All right. Okay. The hot one we can kind of see is turning. What's it color it turning? What is it closer to? The blue one. So what does that mean? Where is triangle on our reaction? On the reactant side. So what kind of reaction is this? And I don't even have to tell you. It is endothermic. Very good. And so you'll study this in LCP next week. You'll do the same things. All right. So have a good weekend. Remember my review sessions tonight. Yeah. Okay. Oh, and the last one I was supposed to do, I was going to add salt, NaCl. If I add NaCl, what's going to happen? Should turn blue. Yes. But it's not very obvious. It's not a good like bright blue like the other one.
After the next 2 hours, let's go to review session.
Yay.
And nap.
Just bring food, bring whatever. McPherson 1045. McPherson 1045. McPherson 1045. It's on our thing.
My friend who's not in chemistry come here because
Yeah.
we plan to study together.
I don't care.
Okay, cool. I don't know. Some teachers I feel like might be weird about that. But then
No,
another
no.
thing, can we look at like my post grad, like
Right now?
where you can,
Yeah.
upstairs where you can see like what I put down and what the correct answer is?
Yes, I can do that.
For
Yes.
the
See ya.
the calculation.
This was good. Yeah, sorry. Oh, there's me. Gross. Gross. Yeah, let's just go right now.